the second half of electromagnetism is obviously the electricity part. And there was this guy named Oersted, okay? And he was basically, I think this was the guy who was simply, working on an electric circuit on his workbench, and he had a compass around, and he figured out, or he noticed anyway, that the compass needle was moving every time a circuit wire was by, okay? So the current can create a magnetic field. Why? How? Well, there's moving electrons in there. And remember, the definition of magnetism is basically you need a moving electron. You need a moving charge. Well, you get this field line around, see, look at these compasses. You get a field line around the wire, and you get the current, right? And I think we'll deal with this later, whether or not the current is going up and down, but let's just say it's going to go that way for now. Okay? You get the current through the line, and the field is perpendicular to that current. Okay? More current, stronger field. If you get no current, if you turn this current off, you get no magnetic field. Okay? So what Oersted was dealing with, okay, is here's his current line, right? Here's current was going that way, okay? Current carrying wire, we dealt with that in the last unit, okay? And remember, and these questions here are pretty straightforward, and I hope you remember them because it's very important now. What does a current carrying wire mean, and how do you get a current to flow through a wire? What were those three things that you needed to have a circuit? Okay? You needed a voltage difference. That means you needed a source of moving electrons. What else did you need? You needed some conductors. Okay? And what else did you need? It had to be a closed path. It had to be a completed path. Okay? And then we talk about what does it mean when you say the direction of deflection. That means this compass. How is this compass going to deflect? How is it going to move depending on the polarity of the current? Which way are things going? If that's positive and that's negative, that means your current's going that way. Okay? I'm going to start to put together a lot of different pieces here, so I hope we can keep it straightforward. How is this used? Well, there's something called a solenoid. Solenoid is simply a long, thin loop of wire. Okay? You loop this wire a whole lot, 10 times, 1,000 times. Okay? You wrap it around some type of metallic core. Okay? So when you pass a current through that wire, when you pass that current through, okay, it's going around, coming back down this way, you got moving electrons. Well, now you have a magnetic field developed. Okay? Remember, the field lines go from north to south. Okay? Sometimes you'll see a horseshoe magnet used. But remember, you need a current carrying wire, and you loop it around some metallic core. The electromagnetic strength, a couple of things that you probably need. You need coils. Okay? Why? It's kind of, the equivalent of being with those electric field lines and magnetic field lines. The more coils you have, right, the closer they are together, the more you have, the stronger it gets. The stronger the strength of the magnetic field is proportional also to the current in the wire. Okay, so you wonder why we've been doing a lot of those calculations. We need to look at that current going through that circuit. You need some type of metal rod at the center of that solenoid, okay? And basically, we're making an electromagnet. And we'll probably build these in class. Then came along this guy, Michael Faraday. He's a pretty cool guy. He was one of those smart electric guys, too. He also figured out, Faraday figured out that you could induce a current. You could induce a current, that's a good word, by passing a wire through a magnetic field, okay? So you would keep these wires stable but move the magnet a little bit, okay? A little bit opposite of what we're up to, and we'll spend a little more time with this in class. So here's the electromagnetic induction. Okay. You got your charge going out. You're wrapped around something, some type of whatever this is, could be just about anything. And then you move this magnet in. Okay, and as soon as you move it in and move it back out again, things start to happen. Electromagnetic induction. Again, we'll spend a little more time with this. But this is fixed, your circuit is fixed, and your magnet is what's going back and forth. How do we use this? These are in a lot of different places, okay? If you ever had a CAT scan, electric motors, the hard drives on your computers, the speakers in your earbuds, okay? When I was your age, our headphones were huge because they didn't have magnets small enough to make small earbuds. And then somebody figured out how to make them really small by putting a little tiny magnet in there. And you went from having those huge headphones to having small earbuds because they found a material to create that magnetic field. Okay, electromagnets. If you play an electric guitar, you know, and if you have an old one, take a look at that pickup. Look at the pickups on an electric guitar. Same types of things are going on. Is that it? Well, we'll have more to talk about in class on these practical uses as well. There's a lot of really cool things here. Electromagnets are all over the place. They pretty much help us get through the day. Okay? But we'll talk about this idea of electromagnetic induction. This is really important. This is in a lot of different places. Okay? And we'll show you how this works. We'll get our hands on this. But you can induce this magnetic field by simply because you have these coils. Okay, thank you much.